This video ultimately is an overview of how to take an image that you find online and use it to continue to explore properties of that region in the infrared. When I originally came up with the concept for this video, it was not long after JWST had launched, and there were some really beautiful images that had been posted to a Facebook group that I was part of, and the person who posted them posted a note that said, "Gosh, this would be a great target for JWST." Well, I took that as inspiration and I made a video taking that gorgeous image and used it as a springboard. I can no longer find either my copy of that image or the original copy of that image, and I fear I may have offended that person originally. So we are going to try something a little bit different. We are going to go for the same target, but starting from a completely different image. I'm not meaning this as offensive. I'm meaning this as using it as a springboard to use images that you find online and teaching you how to use the tools that are out there to leverage your interest in images that you find online to go exploring in the archives that NASA has, but specifically the archives that NASA has with us here at IRSA. The things I want to cover in this movie are the wavelengths covered by JWST and, in contrast, by the data sets held at IRSA. I want to cover how to search for data at IRSA given the name of an object. I want to cover how to attach a world coordinate system to an image using astrometry.net and how to use that resultant image at IRSA. I want to cover how to explore images using IRSA tools, at least the beginning of that. There's lots more videos that go into lots of that separately. I want to cover how to get large tiles of data from IRSA so that you can use infrared images in your own, making your own composite images. And then lastly, how to search for astronomy literature at a given position using Simbad. So, the first step. What wavelengths are we covering here? Well, optical is roughly like 1/10 of a micron to a micron. And infrared is roughly like a micron to like 1,000 microns. Spitzer goes from like 3.5 to like 160 microns. WISE is from about 3.5 microns to about 22 microns. Herschel goes from about 70 microns to about 500 microns. So comfortably infrared. Hubble is of course mostly optical. It also has an infrared instrument on board called NICMOS. But most of the recent famous Hubble images that you've seen are from an instrument called ACS or WIFC3. Where do you think the JWST wavelengths are? They're here. But the images that are really garnering the most of the media attention are actually from NIRCam. So really, really near infrared images. So not very far into the infrared at all. If you're interested in exploring the infrared part of the spectrum, you really do need to get into Spitzer, WISE, and Herschel data. And fortunately, IRSA has a ton of Spitzer, WISE, and Herschel data, and that's part of why I'm making this movie. Okay, so I'm going to work with this image because this is the same region of sky that I was interested in the original image that I had been working with from the original movie. So this black cloud here is Barnard 174. So I'm going to start by going to the IRSA homepage. I'm going to click on IRSA Viewer. There are other tools at IRSA, but the reason I'm sending you to IRSA Viewer is because it gives us access to a wide variety of data that we're going to need in a few minutes. So for images here, I'm going to start by searching for images. I'm going to put in Barnard 174, and it resolves it into coordinates. Spoiler alert. In order to find an image in IRSA's archives that matches the image that we're trying to match from social media, we're going to need something that's actually pretty big. So I'm going to actually ask for a degree. In order to pick what data set to use, it's kind of quickly overwhelming because there's just a ton of data to choose from. But you can use the filters on the left to filter it down to a more reasonable short list of things to consider. Like, for example, if you just want to use WISE data, if you click on that, then it's greatly reduced your choices on the right-hand side. So I'm going to pick WISE, all WISE, and then just for comparison, I'm going to pick DSS here, because with the DSS images, it's going to provide a way of anchoring ourselves back with the optical image that is posted on social media. Okay, so just for those two surveys, I'm going to go ahead and hit search. Okay, it's come back, and you can see, remember, these are reverse grayscale. So you can see that sort of distinctive hook shape is prominent, not just in the optical, but if you know where it is, you can see it in some of the infrared too. It's definitely finding the same region. Barnard 174 is definitely that region there. One of the first things we need to do is link all of these images together by WCS. So we go up here and lock the images together by WCS. And now we can zoom in a little bit, and isn't that interesting? Right away, we can see that there are some bright infrared sources in this dark cloud. The original post back in 2022 was hypothesizing that this might be the site of star formation. And the fact that there are some bright infrared sources in here backs up that claim that, yes, seems likely that stars are forming here. But let's keep going. Let's see what else we can learn. That's the basics of how to search for data at IRSA given the name of an object. But let's see if we can tie it back to this image here. Now, a lot of these so-called amateurs, I mean, they're really good, so they're a lot better than you might think of by use of the word amateur. But a lot of these folks post their original FITS images to the web. But I'm going to work on the assumption that all we have is this JPEG. So what do we need to do in order to be able to compare this JPEG image with the research grade images that we have here? Well, we need to get some coordinates attached to this image. The word for that is astrometry. Not astronomy, but astrometry. Astrometry means assigning coordinates to the image. There's a website called astrometry.net, and it's a service to which you can upload data, and it will attempt to attach coordinates to that image. When you do this, you can actually go to the web form and upload a JPEG or a PNG. And what it does is it takes the image, has a massive database of all of the stars in the sky, and it does pattern matching. It compares all of the stars that it sees in this image, or the bright stars, and tries to match it to its database of stars. So you upload the file, and then it tries to match it, and it gives you an update. In this case, this is a screen capture from when it actually was doing the matching, and it matched pretty quickly. It found a whole bunch of matches with all of these bright stars, so it was able to attach coordinates really quickly. Then you can go over here and download the image here. Now remember that color in astronomical images, or color in any images, is a little bit of a funny thing. The color images that you're viewing on your computer right now are actually superposition of a red and a green and a blue plane. So the color image that we have here is actually 3 planes put together. And astrometry.net, that software knows that. So the image that we get back, this new image.fits, is trying to separate the color planes and does so imperfectly. But that's not what we're here for. We're not trying to conserve flux. We're not trying to do science on the brightnesses in this image. We're trying to figure out where in the sky we're looking. So let's go get the file that I saved from astrometry.net. It's that new image.fits, and we're going to load it in. See, it's got 3 planes. It tried to separate the red and the green and the blue. But look at what it's done. It's already got the astrometry attached here. I mean, this is not a beautiful image. It's certainly nowhere near as beautiful as this is. But it's got the coordinates attached. And the IRSA software knows exactly where it's looking. See, it's aligned this image from the web passed through astrometry.net with all of the research grade data that are here. So it knows exactly where it is in the sky, and it's aligned it with all of the other research grade data that's here. So if I want to figure out exactly how big this object is on the sky, I can do that. Let's make it fit in the field of view. Then I can go over here, get the ruler, and I can measure how far across this is. Remember that the moon is half a degree across, so that is almost 3 full moons across because it's 1.3 degrees. So almost 3 full moons would fit across that way. If you want to change the units that you're looking at there, you can change that. If you go to the overlays, right now it's in degrees. If you want to see it in arc minutes or arc seconds, you can do that. But in this case, because that's a pretty big field of view, degrees is fine. Let's end the distance there. So really, this innocuous seeming relatively small image is actually a pretty big chunk of sky, right? Now, we attached coordinates here, but we didn't attach any wavelengths to this. Let's see what other wavelengths we can find. Let's go back to the Images tab and let's cancel the selections that we had before. Let's go look and see if we can get some Herschel data, because Herschel is really long wavelength light. Let's see if we can get some 2-mass data. Let's get the 6-degree mosaic data. Let's get some IRSA data just for comparison. And just for fun, let's see if we can get some Akari data too, sure. Okay, search. It's found quite a bit of data. Okay, so let's go up to the list of images. And this table here has the wavelength assigned. Let's sort by wavelength. It doesn't know what to do with the data that we attach the astrometry to, and that's fine. But now all the other data is sorted by wavelength. Let's get rid of the failed image. Okay. So now we have a whole bunch of data. Let's make sure that north is up in all of these cases. And we've got the little Barnard 174, and it's lined up for all of these different data. Look, oh my gosh, it's just off the edge. Some of these Spire observations. Okay, so we have Spire 250, but it's just off the edge of that tile. Just off the edge of that tile. Oh, just barely off the edge of that one. Okay, let's go back. Let's see if we can zoom in just again here. Zoom in just a little bit more. So that bright object is really bright. I mean, it's detected at IRAS bands, and it is so dark. It is just not there in the optical. It's even barely there, not really even there at the near infrared. It's barely coming up at K-band. And even at 12 microns, WISE-3, it's relatively faint. But by the time we get out to 60 microns, it's really bright. It's even right there. It's really bright at Akari wavelengths. Even at PAX 100 and IRAS 100, it is really bright. It's off the edge of this tile too on Spire. But wow, this is really a really bright thing. So now, if you wanted, you could make a color composite. Go back over to images and you can choose create a 3-color composite. Now you know what kind of data are around, and you can choose the individual colors that you use for the color planes. Conventionally, you would use the longest wavelength you have for red and the shortest wavelength you have for blue, but you don't have to do that. You can do whatever you want. And when you have something in the results, you can change the color planes. You get a color stretch here. When you have a color image, it'll give you the histogram for the red, green, and blue separately. So you can change the color stretch for the red, green, and blue separately, and you can manipulate the data to bring out whatever highlights you want to bring out. You're not changing the data, you're just changing the way it's represented on the screen. Let's go see if anyone has cared about this object before. Let's go up here and choose rectangular selection. Then we can go and draw a region around that object, and then go here, and then go to Simbad and search. Look, we've got lots of things here. I'm betting that IRAS source is the bright source, because it was so bright it was visible even for IRAS. So it's a long period variable candidate. So maybe it's not a young star. Maybe it's a red giant. Don't know. There's 7 references between 1850 and 2025. So I don't know what it is. We're going to need to go digging into the literature and figure out if anyone has cared about this object before in any detail. It's really bright and it's within a dark cloud. So maybe it belongs to the dark cloud. Maybe it's far behind it. I don't know. We're going to have to go exploring and see if we can figure out what this thing is. I wonder what its SED looks like, because you can get the fluxes for all of these things. You can go to the catalogs tab and then start pulling the fluxes from all of these catalogs for this target. And then you can create a spectral energy distribution and see if you can figure out what the spectral energy distribution looks like for this thing. You can even go and get light curves for this thing, because you're not going to get anything for ZTF for the light curves because it's way too faint, but you will be able to get light curves from NeoWise because we can see it in the WISE data. So we should be able to get NeoWise light curves for it. We can try and see what kind of variability this thing has at 3.5 and 4.5 microns. If it says it's a long period variable candidate, I bet it's variable and wise. So lots of interesting things to go tracking down, including things from literature. Okay, so let's go back to maybe the wise 3, one image at a time. Now the original post said something about maybe we could get JWST time for this. Let's see if that's feasible. So we can go up here and add a JWST MIRI footprint. Look how tiny that footprint is compared to the size of this cloud. Even if we were to just cover this cloud, imagine how many pointings we would need of MIRI just to cover this cloud. Let's see if we can do, instead of MIRI, let's do NearCam. Even with NearCam, it would take us many pointings to cover this entire cloud. We would need a lot of JWST time to cover this whole cloud. It might be reasonable to cover just this target, but we would have to write a really compelling proposal even to get JWST time to observe just this target. Because JWST time is pretty competitive, so we'd have to make a really good case. I don't think we'd get time to cover the whole cloud. Honestly, I don't think we'd even get time to observe this object, unless we could make a really good case that it was some innovative, new, and different object for which we absolutely needed JWST time to explain. So there's lots and lots of information online. There's all sorts of online help that talks about how to use these tools, but at least this gives you a tip of the iceberg introduction, a crash course in how to manipulate data and how to grab and use some of the data that you find online and how to access some of the data here at IRSA for any given target that you find online.